Hello, I'm John Gertz, SETI theorist, and today I want to continue our discussion of the Drake equation, drilling down into the one factor in the Drake equation called F sub p, which is the fraction of stars that have planets. Well, Frank Drake, when he devised the Drake equation in 1961, had no idea. We do today. We know very well that the fraction is equal to 1. For all intents and purposes, all stars have planetary systems, and not just single planets, but whole systems of planets. In that respect, our solar system is typical. Why do we say this? There are two basic bodies of evidence that support this contention. First, there's star clouds or dust clouds that are forming new nurseries of stars like the Orion Nebula or the Eagle Nebula, made famous by the Hubble and then James Webb Space Telescope pictures of the pillars of creation, as it's called, which is a star nursery. They're big clouds of gas and dust that are coalescing down into brand new stars. And whenever astronomers have looked at these protostars, these brand new stars in the making, they invariably see circumstellar disks of matter, disks of matter that orbit the stars, and from which it is presumed planets are in the process of being formed. The second great body of evidence in support of the notion that F sub p equals 1 is that evidence deduced from the Kepler Space Telescope. Now, the Kepler Space Telescope mission, the main mission, the first mission, lasted 4 years and looked at 150,000 stars in a single wide camera view and discovered approximately, to make the math easy, 4,500 stars. Now, the way it did this, let me just say first that the math becomes easy, so that if you divide 150,000 stars by 4,500 planets that have been discovered, you find that 3% of all of the stars harbored planets. We'll come back to that in a second. But first, I want to tell you a little bit about how it discovered these planets. So when a planet passes in front of the star relative to our line of sight here on Earth, it will dim the starlight by a little bit. If the Earth were to pass in front of our sun relative to an alien's line of sight, it would reduce the sunlight by approximately 1/10,000th, just a tiny factor. If you see the dimming of a star by a factor of 1/10,000th or 1/20,000th or 1/1000th or whatever it is, it doesn't mean a darn thing if you only see it once. Could be a sunspot. Could be something else. And when you see it twice, it could be two sunspots. But if you see it a third time with the same periodicity, in other words, the space between time 1 and time 2 and between time 2 and time 3 is exactly the same, that's indicative of a planet. Because only planets and not sunspots come around exactly at the same time. So from this, Kepler found that 3% of all the stars in the star field had that sort of dimming, from which they could be deduced that planets went in front of the star. But that doesn't mean that only 3% of stars have planets. No. This is a vast undercount, because only approximately 1% of the possible orbits of planets will cross their star relative to the line of sight of Earth. So if the orbit of the planet is going in some other direction rather than directly in front of our eyes, we won't see it. And only 1% of the possible orbits will transit or will cross our eyesight. So scale this up by a factor of 100. So now we're not talking about 3% of all stars that have planets, but rather, 3 planets per star. But this too is an undercount because remember that the Kepler mission lasted only 4 years, and it takes three circuits in order to define or at least three circuits in order to, or three orbits at least to define a planet. But that means that Kepler couldn't find any planet further than the Earth, which takes 1 year, plus a little bit more, somewhere between Earth and Mars. And that's it. So if an alien was looking at our solar system, it wouldn't see Mars, Jupiter, Saturn, Uranus, or Neptune. But even then, this is an undercount because that same alien, if they had exactly the same telescope from the same distance and so forth, looking at us would also not detect Mars, Venus, and Earth because they were too small. They blocked too little sunlight in just the number of orbits that took place within 4 years. So in other words, Earth is not quite large enough for the Kepler to have detected with just 3 orbits. It would take more in order to distinguish the data from the system noise. So the case for F sub p worsens when you realize that the census of planets in the Drake equation also neglects moons and dwarf planets. Dwarf planet being, for example, Pluto in our system. There's no reason to believe that life cannot have started on a moon, and indeed, there's intense speculation here in our solar system that life might possibly have arisen on the moons of Jupiter, Europa, Callisto, Ganymede, or on the Saturnian moon of Enceladus, or Neptune's moon of Triton, or Uranus's moon Titania, and so forth. So that too limits the sense, the value of F sub p, considering just planets and not also moons and dwarf planets. The bottom line is that planets are ubiquitous and planetary systems are ubiquitous, such that when any factor in the Drake equation is 1, it can be taken out. It's useless. It doesn't give us any added information. It's like walking into a hat store. It may help me if I'm looking for a green baseball cap to know how many of what percentage of the hats in the store are green and what percentage of the hats in the store are baseball hats. But it doesn't help me at all to understand that what percentage of hats are hats. Obviously, 100% of hats are hats. Anyway, so much for the F sub p. Can come right out of the Drake equation. It's useless. It doesn't mean anything anymore. And with that, I'll close today's video. Thanks for tuning in, and don't forget to visit my website, johngertz.com. Until next time.